Okay, before we actually begin, let me just recap with you guys. Can you all still remember the meaning of a linear recurrence relation, the meaning of a homogeneous linear relation? Can remember or not?
Can.
How about the order of your linear recurrence relation?
Got how many terms?
Got how many terms? Not exactly got how many terms. Okay, so the order is especially important for things like this. Take note. There's only 2 terms, but this is order 2. Why?
Because
That's only.
relationship.
Okay, for first order means that the the relationship is 1 term away. un minus 2 versus un minus 3. This one is 2 terms away, un versus un minus 2. That's why it is order 2. Okay, then linear or not linear, simple. Look for the power. Homogeneous or not homogeneous, the indicator is whether you have a number or you have a 0. Okay, so this is basically what you have so far. So now you know how to basically recognize your recurrence relation. You're ready to actually solve the first order linear recurrence relation. So take note now, we're handling only first order linear recurrence relation. So one look, this is first order. This is your first order linear relation. Okay, so the green section is your first order linear recurrence relation. So your job in example 9 is to verify that this xn is equals to 4n, as for xn equals to 4 power n minus 1 is one of the solution to this. Okay, so what you need to do is, starting point is which one? Yellow or green as your starting point?
Green.
Green.
Okay, your green should be your starting point. So if this is a verification question, the typical approach is the left hand side and the left and your right hand side. Left hand side and right hand side. Hey, where's my page? Lost already. Where is my page? Gone. Okay, 在哪里? Okay, good, here. Okay, so as I was saying, this is the left hand side and this is the right hand side. Okay, so consider the left hand side first. So left hand side, you actually have xn. And what is xn? Xn is this. So this is why you see this in your solution. Left hand side is xn, and xn actually comes from this. Okay, thereafter you consider the right hand side. Right hand side is actually this. So I want you to focus on this section that I'm highlighting in yellow. X, okay, subscript n minus 1. Okay, x subscript n minus 1. So how do I move from this line to this line? Is that I have replaced my x subscript n minus 1 by 4 to the power n minus 2. Can you understand how I do this? If this is xn minus 1 is basically 4 n minus 1 n minus 1. So that's how I get my 4 to the power n minus 2. Simplifying it, I'll get 4 to the power n minus 1. Can follow the flow? So what you have just done is left hand side is equals to right hand side. So you have done this verification. So this thing, okay, xn minus xn equals to 4 power n minus 1 is a solution to your recurrence relation. Can understand so far? Take note, there is a reason why we highlight this word 1. Okay, can you please highlight first? Okay, can you please highlight first? So far so good? Okay, let's move on to example 10. Okay, then you'll be able to understand more of your recurrence. Take note of the question. Now they say find the general solution to the same recurrence relation. Okay, so what I want you to do now is spend some time understanding the difference between example 9 and example 10. In both examples, the recurrence relation is the same. It's the same recurrence relation. In example 9, they ask you to show that this thing, 4 to the power of n minus 1, is a solution. But this time around in 10, I'm asking for the general solution. Okay, so that's the difference. One is find a or show a solution or find a solution. This time around I want a general solution. It will work for all positive integer n. Can? So what I need to do next is, again, my start point must be my recurrence relation. This is my start point. For xn is equal to 4 subscript n minus 1. Then I'm going to operate on my n minus 1. Okay, so how I'm going to operate on this is, if this is, hang on, if xn is equal to 4 subscript n minus 1, what is x n minus 1? It will be 4 x n minus 1 minus 1, which is 4 x n minus 2. Can understand?
Yep.
Okay, so that's how I get my first line. 4 times 4 subscript x subscript n minus 2. And then what happens next is I factor out the 4. So I got 4 square. Then I have this thing, x n minus 2. So based on this recurrence relation that I have, can you give me what is 4n minus 2? Sorry, what is xn minus 2? It will be 4x n minus 3, right? Can you understand so far? I'm going down the line. So this will become this whole section in blue. So basically I can go down the line. I can go on and on and on and on until the last term. So where is the last term? Where is the last term?
Can you go to x0? Or do you stop at x1?
So how do I know where's the last term? Look at the question. Positive. So the last term must be x1, right? Okay, so that's how I decide what's my last term. So my question to you now is, you see, there's nothing for you to copy. So my question to you now is, do you have the ability to spot pattern and give me this general result? Spend some time thinking through. Okay, to some of you it's very easy. To some it doesn't matter. It doesn't make sense. Here you need to spot pattern. This is 2. This is n minus 2. This is 3. This is n minus 3. So if I want x1 is for what? You will need x to the power of n minus what term? N minus 1, right? Then I can get x1 to appear. So if this is n minus 1, this must be n minus 1. Can understand? Okay, nothing to copy. So my whole issue here is, are you able to generalize and give me this result? Anyone have problem? Anyone have problem? Okay, no problem. So now what you have is actually this xn is what we call the general solution. Okay, it's the general solution. And just now in your example 9, you have 4 to the power n minus 1. This is a particular solution. Okay, this is a particular solution when my x1 is equals to 1. So the whole idea here is I'm introducing to you two important terminology or definition. One, we're talking about general solution. The other one, we're talking about particular solution. So again, let me reiterate one more time. What do I mean by general solution is, this is general. general to the sense by which as n changes, I can get various values. So let's say I want to find the 10th iteration. What's x10? x10 will be 4 to the power 9 multiplied by the first term. So this is general. Then if I know a particular value, so let's say if x1 is equal to 1, then x10 will be just 4 to the power 9. But if x1 is equals to 2, what is x10? x10 will be 4 to the power 9 multiplied by 2. So particular solution and general solution. Particular solution only works for certain instances if I know what is the first term. First term can be 1, first term can vary. General solution is general enough for you to accept anything as your first term. So far so good. So far so good. Can Okay, so what you have just gone through with me is actually what we call the backtracking method. I backtrack until you actually arrive at the lowest possible term. Okay, there are a few other methods in order for you to learn to get the solution to your recurrence relation. First order linear recurrence relation. Okay, so one more time, we try the backtracking method. Okay, if xn plus 1 is equal to 3, xn minus 2, I want you to find xn in terms of n. Technically, I'm asking for the general solution. Are you able to do this? Can you don't look at the solution, try yourself? Can you please take out a piece of paper, try it? Okay, because it's a process that you actually need to learn and go through the rigor. Try. Okay, so the typical approach is basically, of course, start off from the recurrence relation, then do your substitution bit by bit. Okay, and then you try to spot some pattern and generalize until you can get certain patterns coming up. Can or cannot. Okay, this time around the pattern is not so straightforward as your example or example 10. Okay, this pattern involves a little bit more skills that you have actually learned before in your GP. Okay, the pattern observation skill. Okay, if you are, as I said, you don't have to copy anything, everything printed out for you. So this is your important critical step. Anybody needs me to explain the pattern? So of course, what you need to do is realize this is 3 and this is 3. In order for you to get 1, okay, you must have a n minus 1 on top. And then there's a second set of pattern here. Okay, this is a clear-cut geometric progression. Okay, clear-cut geometric progression. And then what you're going to activate here, can you please write down, is actually your sum of GP formula. Okay, your sum of GP formula is A1 minus Rn 1 minus R. Okay, and once you generalize out everything, you will be able to give me this expression. Any problems? Any problems? Okay, so let's talk about definition again. Is this a general solution, or is this a particular solution. Which one is this? Hello, still there? General or particular? General or particular? You need to get this clear because later on, as you move on to second order, or don't even need the next one, the next page only, you're gonna have some problem already. General solution or particular solution?
Particular.
Particular, why?
Put the x1 equals to 3.
Yep. Okay, I've actually substituted x1 by 3. So if I ask for general solution, what should you be writing instead?
Leave it as x1.
Yep. So if I want a general solution, can you please write down? It will actually be 3n minus 1, x1 minus 2, 1 minus 3, n minus 1, 1 minus 3. Okay, that will be your general solution. General solution here, particular solution. So in color, this is yellow general. Green is particular solution.
Do you need to simplify it?
You're talking about which one? General solution? Are you talking about general solution or particular solution?
General. Do you need
General, yeah, of course. This one
your
must
question?
simplify further. This one must simplify further. And then thereafter you get your x20 is going to be quite straightforward. So far so good. Okay, so this is your backtracking method. So you will be activating this technique in your tutorial question. Okay, that I thought that you could do yesterday. Can then okay, there'll be some people who tell me what's the point of doing all this. I can actually backtrack. Correct. You can actually use your calculator. Make sense? To find your x20 using your calculator technique. But it's not going to work for all the time. Okay, so when you actually do this, technically writing out everything, some people can actually observe this kind of pattern coming out. So this kind of method, I would just say, please forget it. Okay, it will not work half the time. Not say half the time, all the time in the exam. Will never give you an expression that's so easy to do. So far so good. Okay, so I have settled the number. Okay, number as in I've gone through one example involving physical number. Now I'm going to generalize for you now with all the unknowns. So when we do generalization, first order, linear recurrence. This time round I got no numbers. It's all in terms of variables. Xn plus 1, x to the subscript x subscript n plus 1, a multiplied by xn plus b. So I'm asking for general solution in terms of all your variables here. Okay, so I'm asking for general solution. So the technique by the backtracking method is exactly the same, just that I got no numbers. It's basically one whole mess of variables. Okay, so the process exactly the same. So what's happening here is exactly the same as what's happening in example 11. Only difference, I got no number. It's all in terms of variable. Then after you do this, same technique comes in, spot pattern. Okay, you need to spot the pattern, and then you realize that you end up with this followed by your GP section, exactly the same as example 11. And once you factor out everything, you're going to get this as your general solution in terms of all your variables here. So far so good. So far so good. So what you have here is something for you to memorize. Okay, so the bad news now is you may need to memorize this general solution. Okay, but half the time nobody can memorize this. Okay, so if you look at your tutorial from your question 2, question 3 of your tutorial question, right, you can actually just write down the answers for the general form if you can remember this formula. But I will never recommend this because nobody can remember this formula in the exam. Okay, but if you can actually remember this, you can memorize this, and if such a question number 2 and question 3 appear in your exam, you write down the answer, I have to give you full marks. Okay, understand? Okay, so this is your first general solution of any first order recurrence relation in the form of AXN plus B. Can? So let me ask you some fundamental question now. This one. Let's go back to your fundamentals. This is a first order linear recurrence relation. Next question is this homogeneous or not? Is this
Not
RR?
homogeneous.
What's homogeneous? Go back to your definition in front.
No constant.
No constant. So not homogeneous, right? Not homogeneous. So my question to you now is, if this is a first order recurrence relation, it will work for homogeneous and non-homogeneous case. Agree? If it's homogeneous, B becomes 0, your solution still appear. It's just, so what's your answer? Your answer, your general solution will just be this. If it's non-homogeneous, you have this section coming in. So far so good? Anyone not clear what's happening? Can you please write all these little bits to yourself? Okay, plus B means it is, if B is 0, it is homogeneous. B not equals to 0 is non-homogeneous. So it will work regardless. Okay, as long as it's a first order RR, first order RR, whether homogeneous, non-homogeneous, this will be the same general solution. So far so good? Okay, so now let's tackle the same thing now. But I'm not going to use the backtracking method now. I'm going to do the convert to GP method. Okay, I'm going to do the second method. Okay, but usually this method is bullshit lah. Half the time you cannot be applying this in the exams. Okay, so recommended method is still method 1 so far. Okay, so follow instructions. Show that this can be written in this form, where k is equal to this. So basically I'm just asking you to rewrite it in certain expression. So what you need to do now is start off with this expression. Okay, because your job is to show that the green can go to the yellow. So I must start with the green. Then what I do next, follow me line by line, okay, because you may not be able to follow. Next is I'm going to subtract k on both sides. Okay, subtract k on both sides, and then now you focus only on the right hand side. Now what has happened to the right hand side is that I factored out your a from the right hand side. Okay, I factor out the a from the right hand side. Thereafter, what I'm going to do now is make use of the result in yellow now. So what I have is, for this xn minus k to be written in this form, what it means is that I'm going to do a comparison. That means this must be compared with this. Okay, so if this is true, what it means now is that the blue, the blue color, this blue color must be equals to this blue color, and that's how I get my next expression. Then you shift around, make k the subject, you will be able to tell me that k is equals to b over 1 minus a. That's how you prove the first part. So far, so good. Okay, nothing really fantastic, it's just playing with your algebra. Can? Okay, now let's go to part B. If I were to let un to be xn minus k, where does xn minus k come from? Is actually this section, xn minus k. Okay, so what it means is that un is actually a n minus 1. A un minus 1. Can you tell me how does this happen? Basically, this is un. This one will be un minus 1. Can spot the pattern? Okay, so it's basically a matter of replacement. Replace this by un, replace this by un minus 1. So I have this un, this yellow bracket here. Un is equals to a un minus 1. So far so good. So next thing is, can you accept that this actually is an indicator that you have a GP coming out? Can you accept that this actually is a geometric progression? Un is equals to AUN. Okay, this is a geometric progression. So if this is a geometric progression, the nth term of a GP is actually un is equals to AR n minus 1. Okay, the nth term of GP is actually u is AR n minus 1. So what I'm going to do now is I'm going to say that un is equals to a r, this is my r, n minus 1. Okay, say again, u1 is my first term. The common ratio is a. The number of terms will be n minus 1. So far so good. Can? Okay, so after this, let me erase off. What you need to do next is, I have xn minus b over a. b over 1 minus a, which is what result? This result here. Okay, this result here is equals to a this one is u1 is actually where is it? U1 is actually x1 minus b over 1 minus a. So far so good. Multiply by my an minus 1. So far so good. Then of course what you need to do next is push it across. You have express it, make xn minus 1 xn as the subject, and you have the same result coming out. This general solution is exactly the same as what you have in your example 12. Okay, exactly what you have in example 12. Okay, this method of proving is what we call conversion to the GP method. It is absolutely stupid and absolutely crazy. Half the time nobody will be using
Can
this.
go through the record nth term of GP that line.
Okay, recall nth term of GP. Okay, hang on, let me remove everything. Okay, so up to here you can accept this one in green. un is equals to a un minus 1. Can accept? Can accept this? un is equals to a. Okay, so next, if I can actually recognize this is a GP, okay, what it means is that I can actually activate this formula in blue that I'm highlighting now, because this is the general, the nth term of a GP. un is equals to a r n minus 1. Can. So what I'm going to do now is, what is a? First term, u1. Makes sense. That's how I get this. Follow so far? Then if this is the GP,
Oh, I get it.
yeah, the common ratio must be a. This is the common ratio. This one is your a. And then your n minus 1 just follow through. So far so good? Okay.
Yeah.
Okay, so procedure wise, okay, I said we have actually listed out the steps for you. Step 1, convert to this. Step 2, convert to this, step 3, etc. Okay, but this, what you call that? This way of finding the general solution of a recurrence relation is actually quite stupid and quite dumb. So most of the time, I will not be using this method, and I also don't recommend you using this method. Can? Okay, so just practice with you one example using the conversion of GP method. So consider the sequence. This is what you have. Now I'm going to give you first term is 3. Express xn in terms of n. Okay, so if you run through the process, you will tell me that this is the question. Then un plus 1 is equal to 3 un, where un is equal to this and your k is equal to this. Okay, this is provided you can remember everything down there. Okay, this is provided. Okay, you need to be able to memorize all these things that comes out from here. But if you cannot remember anything, this method will not work at all. Okay, it is very, very fast for you to write down the general term. This example is exactly the same as your example 11. So if you recall how you actually handle 11, let's scroll back. Okay, how I find the general solution for example 11 using the backtracking method. Okay, we basically backtrack, and then we spot pattern. Remember? So the process is actually quite tedious, but it's going to be dead. It's a dead process. All you need to do is spot pattern. Whereas you look at the solution for example 13, which is exactly the same question. The solution is just a 3-liner, finish. But that is provided you can recognize, or you can remember, oh, you have this k value, you can remember this general solution. But if you cannot remember the general solution, it is impossible for you to arrive at this answer so quickly. So far, so good. So far, so good.
Yes.
Can So as I said, half the time nobody will be using this, because tutorial, yes, I agree that you can just shortcut and give me the answer, but this method is almost not replicable in the exam. Okay, this method is almost not replicable in exam, so my advice is understand enough. Don't use this at all. It will not be actually very useful. Can? Okay.
So there will never
Say again?
So there'll never be questions that like we have to use this method. Every method we can do by backtracking.
Yeah, okay, there will never be a question by which actually I restrict your method. Say that I will say, oh, find using the conversion to GP method the general solution. I will never ever do this. No question will be said this way. They will just say, find the general solution. The method, we leave it to you. Can? Okay, So my time is almost up. So I have one little bit things to introduce to you. So take note, I have a complementary solution. I have a particular solution. Okay, so anybody actually can understand what's the meaning of complementary solution and a particular solution. And then later on, right, you have this thing, blue color, general solution. Walao, what the hell? So many things coming out. So just now you went through the definition of a general solution. We went through the definition of a particular solution. Now suddenly I got a complementary solution. Anybody know what's happening? Anybody knows what's happening? Okay, so let me explain. Complementary solution means it's just a part of the solution, not the full solution yet. Okay, so in general, this is not 100% true for all cases. In general, a general solution comprises of a complementary plus a particular solution. Okay, a general solution comprises of a complementary solution plus a particular solution. So what you see here, this one, This is your complementary solution. Plus a particular solution will then arrive at your general solution. Again, so this is the little bit that I'm going to go through today, just to introduce to you in general how all these things add up into your general solution. Again, so spend some time, okay, go through this little bit of the solution since you have all the answers printed out for you. See whether you can understand or not. Then next lecture, when I see you face to face,